Hi everyone, I'm Ruth Trundley. I'm delighted to have been asked to talk about some of my current thinking about teaching and learning mathematics. And I've chosen exploring computational fluency, connecting structures, strategies and symbols, because it's a bit of a recurring theme in my work with learners in primary schools. So fluency seems to be a good place to start and to give you an indication of what I mean by fluency. I've taken this from a publication we wrote a few years ago called No Nonsense Number Facts. And as you read that, what you'll notice is that it starts with understanding. So understanding, from my point of view, underpins fluency. And then you use that understanding to do a number of things. And we've just identified three things here that we think are really important. That you notice things. So one of the things about being fluent in mathematics is that when you're faced with a new piece of mathematics, you look at it and allow yourself and expect to see if there's anything to notice. What do I notice about this? And then you make connections between what you already know, what you've noticed, and what you're trying to work out, the problem is that you're trying to solve. And that leads you to making decisions. So for me, those are really important things within fluency. So as I go through talking to you about this, I'm going to draw quite heavily on a research project that we reported on the first phase of 3 years ago called Understanding Structured Number Lines. Unfortunately, phase 2 was disrupted by the pandemic, but we've got the findings from phase 1 and I'll be using those today. And I think it's really important for me to share where I'm coming from in terms of my beliefs about teaching and learning mathematics, because that's going to underpin and run through everything that I say during this session. So this is a core belief that thinking is at the heart of mathematics, so should be at the heart of mathematics teaching and learning. So that means what I'm interested in adults and children and the way that they think about mathematics and how we support people in their thinking about mathematics and developing that thinking. So that's going to be the thing that I'm going to be looking at. So when we're thinking about exploring computational fluency, what I've decided to do is to take a focus on subtraction and actually spend quite a bit of time looking at one subtraction, but use that so that we can look in the detail to then be able to think about more general ideas that apply across calculation. So I'm going to put a subtraction up on screen, and what I suggest you do is that you pause and you yourself solve that subtraction and you notice how you decide to solve it, because you will be making decisions. And then just give yourself a chance to think about what did you know and understand that allowed you to make those decisions. So here's a subtraction. You might want to pause. So what we're going to do now is we're going to watch a year 4 child working on that subtraction. And in the same way that I asked you to observe your own thinking, I want you to see, as you watch this child work on it, what you notice about their thinking and about the way that they approach this subtraction. I'm just going to move to that now. Okay, so if you could work out 603 subtract 598, off you go. I'm going to watch. Okay.
Happy?
Yeah.
Yeah. Okay, so I don't need to ask you to draw something to show me how you did it, because I think the way you've written it shows me really clearly. But you just want to talk through, because you changed your mind, didn't you? You were going to do it one way, and then you changed your mind. So do you want to just talk me through what your thinking was?
I was doing. I was trying to work out the sum by doing column method, but then I realised that you can't minus 8 from 3, so I went to the next column to take away one of the tens, but then I realised it was a 0.
Yeah.
So it wouldn't have worked. So then I thought of doing it another way, and I did 603 minus 500 and worked that out. Then I worked it out, and it was 103. And then I did 103 minus 90, and that was 13. And then I did 13 minus 8.
Which of those three? So you ended up doing 3 calculations to do your one there, didn't you? You've written them all down beautifully. Which of those 3 do you think was the hardest?
Well, I thought the first one was the easiest.
Yeah.
And then I think this the second one was a bit harder because you had to bridge down into another column.
Yeah. Yeah. I saw you spent quite a bit of time thinking about that second one, didn't you? And I was thinking that was probably the trickiest of the 3 because of that going across the boundary thing. So if we look at that calculation, 603 subtract 598, and you found the answer to it, can you put it in a context or a story? What might the story be that would give us that calculation?
Maybe there was 603 bars of chocolate, and I ate 598.
Does that feel like a realistic story to you, Rory?
Well, my mum would obviously tell me no.
Do you think you could eat 598 bars of chocolate?
Well, I bet I could, but without being sick would be a bit hard.
I think without being sick would be a bit hard as well. Oh dear. If you look at those 2 numbers, do they look close together or a long way apart?
Like a really long way apart, because one of them's 1 digit and then the next one has 3 digits.
Are you looking at the 603 and the 598, or the 5 and the...
Oh, the 5 and the 603.
Oh, okay. I meant the 603 and the 598. Oh. Sorry, I wasn't clear. Do they look close together or far apart?
Really close together.
Really close together, yeah.
Oh, I just realised another way I should have done it then.
Oh, go on then, Rory.
I should have tried to take away, just keep on taking away until I get to 598.
Would that have been quicker, do you think?
Yeah, much quicker, I think.
Oh, well, that's...
Okay, let me just... So I just want you to think about the observations that you made there as the child was having to go at the same calculation that you were working on. Okay. And these are the observations that I just want to share with you that I made. And the first one is about the going straight to the formal written method as the first choice. And this is something that we've seen a lot with children in primary schools, that once they've been taught the written method, they treat it as their default method, if you like. In the literature around executive function and thinking about inhibitory control, this is called the prepotent strategy. So what children do is, rather than stopping, noticing, thinking and deciding, all parts of being fluent, they go, it's a subtraction, oh, formal written method. It's a default. They go straight to it. And we saw Rory do that there. And certainly that was something that was very common in the structured number lines project. So here you can see some more examples of this happening. And quite often getting the wrong answer, which is one of the interesting things as well that happens with this. So one of the things we found in that project was that too many children relied on either counting or a formal written method for both addition and subtractions that could be better solved mentally. And with subtraction in particular, not choosing to focus on the gap between the numbers, not understanding that they should be focusing on the gap between the numbers, or that's one way to think about it. And that often resulted in incorrect responses. I'm not going to sort of spend a lot of time thinking about executive function, but that's where inhibitory control comes in. It's about suppressing that instant response of, oh, I always do these like this, and allowing yourself to make a decision. So this again comes from the summary. This comes from the report, from the summary of findings, and that if we're thinking about children being fluent, they need to be able to be flexible. And what that means is they've got to understand and connect different ways of thinking about numbers and operations in order to be able to be flexible. And one of the things that we felt from that project that not enough attention was being given to making that connection, nor the importance of making informed decisions that take into account the numbers involved. So in the case that we saw with Rory, an informed decision taking into account the fact that 603 and 598 are really close together. And one of the issues that we find sometimes with what's happening for children is that they are being expected to use a formal written method before they've actually secured understanding of the operations. And then that's one of the reasons it becomes their prepotent strategy, is because that's what they understand, they are expected to do, and they don't have the other understanding there to fall back on. And Russell talks about the fact that there's growing evidence that once students have memorized and practiced procedures without understanding, they really have difficulty bringing meaning to their work. So that's quite a concern. So there's something there for us to think about when we introduce and how we introduce written methods. And then some other observations just about watching that video. First of all, that the child we were watching had multiple routes to the solution. And that's really something to be really pleased about, that actually having abandoned the first choice, he had somewhere else to go. He had another place to go. But I think it's interesting if we think about what he did choose to do and how he was talking about the subtraction when he chose his context as well, and even when he noticed that he could have done it another way at the end of that clip. All the way through, he is talking about subtraction as taking away. He may not be using that language, but that's what he's talking about it. So if you think about what he did, he took away 500, then he took away the 500, then he took away the 90, and then he took away the 8, and that's how he talked about it. And then his context was eating bars. So they were being taken away, they were disappearing. And then when he noticed right at the end there was another way, what he said was, I should have kept taking away until I got to 598. So even when he realized he could look at the gap, he looked at it from 603, what have I got to take away to get to 598? So my question that I want to explore now is, what are the barriers to making the decisions to solve this calculation in the most efficient way? And therefore, what might we do about that in classrooms? So I've started and I've gone to look at something by Vinna here, which I've only come to recently to looking at this. And Vinna talks about the difference between concept and pseudo, or conceptual and pseudo-conceptual. And this is the distinction that is made here, that conceptual behaviours, when we've got real conceptual behaviours going on, words are associated with ideas. There's different things, different notions that are connected to those words. But in pseudo-conceptual situations, the words are just associated with words. There's no ideas. And if you think about sometimes how good children get at parroting words without having any understanding, but they've learned to say the right thing, but there's no understanding behind it. That's what we've got going on here. But I think one of the things that I'm seeing emerging from the different work that I do is it sort of extends this. So I want to suggest an extension to this. And I want to bring words and symbols into this, because these symbols are such an important part of mathematics, and we see the same thing happening. So what I want to suggest is that In mental processes that produce conceptual behaviours, words and symbols are associated with ideas. So, you know, we see the symbol subtraction, and there's a whole range of ideas that we connect with that, as we do with the word subtract. Whereas mental processes that produce pseudo-conceptual behaviours, words and symbols are associated with words and actions rather than ideas. So my action is, oh, I take away. My action is, I set it out like this. So there's an action that goes with it as well. But it's about just doing. It's not about understanding. It's not about thinking and noticing and connecting lots of things together. So this sort of link with thinking about the symbols with the words takes me back to Gray and Toole in '94 and their perceptual view of simple arithmetic. And they were talking also about how important symbols are, and that symbols are in fact, as they put here, the source of both success and distress in mathematics. And this is because of what I've just been saying, that for some people, the symbols represent a range of ideas. They have connected in a whole range of ideas and understanding to that symbol. And for others, they are very one-dimensional. So what they talk about here is that those who are flexible and work well with mathematics, they use the same symbol to represent both a process and a product of that process. And we've got an example from their paper here, which is 5 add 4. So that represents both the process of adding. What am I doing? This is doing here, isn't it? How am I going to find 5 add 4? Oh, I might find it by counting more. I might find by counting on. There are different ways I might do this, but there's an action, there's a process that could be involved. But it also represents a relationship, a whole concept of sum there. And so what they talk about, and they term this, you know, this perceptual thinking, this ability to manipulate symbols really flexibly so that you can think about them as a process, you can think about them as a concept, and you're moving between the two. And that flexibility with symbols is something that we need to think about. Are we building that with our learners? And that sort of focus on the symbols takes me to another model. And this is one that we've adapted from Haylock and Coburn's work. And in their work, they were looking at how young learners develop conceptual understanding of you know, sort of a mathematical idea. And they sort of noticed that there are different experiences, different representations of that mathematics and that mathematical idea that children need to experience and connect together. And sometimes this is referred to as the connective model. And so you'll see symbols sitting in there, and every element is connected to every other element. But one of the things that we've been noticing in our work is that those connections are not all equally strong, and very often there's a disconnect with the symbols. And it looks a little bit more like this, where there is not really a connection to context. There's not really a connection to the mathematical images, which may be concrete, and they may be diagrams and drawings. And there is a very simplistic connection to the language, which is often language as a label for the symbol. So I see that symbol and I say take away or minus. It's the Vinner thing. It's just a label. It's just a word associated with the symbol rather than an idea behind it. And I want to just sort of show you an example of this from some work I've done recently with some children in fractions. So I was working with some year 4s, and we were looking at the connection between the division and unit fractions and what happens when you the relationship between different unit fractions, if you like. So we'd taken the context of a bar of chocolate. One of the things about that is it's a common experience. People understand sharing food. And also a bar of chocolate can be represented by a rectangle, that we can have multiple identical rectangles to help us think about different situations with that chocolate bar. So it leads to a nice modelling and allows us to look and compare the fractions that are appearing as we explore this. And with these children, we've looked at sharing the bar of chocolate between 2 people, sharing the bar of chocolate between 3 people, and I'd modelled the number sentences, if you like, the calculations that went alongside, and they were doing the drawings, and we were talking about and connecting their drawings. They were labeling the parts of their drawing and connecting all that back with the context. So we got to this situation, and you can see what they've all done now is they've all been able to write the calculation for themselves. They've all now understood how to record symbolically what's gone on. So it's following, obviously it's following a pattern, and you see they've all labelled their parts there. But then what I did was and actually what might happen there, what could happen in a classroom is that we go, that's okay then. They've understood, they've got it. Look at that, they can all write the calculation and they can all produce the diagram. So we're there, we've got that understanding. But that's not where I stopped with them. I went to the symbols and I said, well, we now need to explain that in the context that we were talking about. Let's go back from those symbols. Remember the connective model. So we've got the situation and we've talked about it and we've drawn it and we've used the language and the context and we've got a mathematical image. So now we need to connect all of that to the symbols, or we need the symbols to come back the other way. We need to come back the other way from the symbols. So this is the coming back the other way. So here's the calculation. They could all read that. 1 divided by 4 equals 1/4. So tell me how is that connected to our situation, our story, if you like? And this is where it gets very interesting. So the first person says, well, it's 1 bar of chocolate. So that's the first bit of information there. And they're thinking about that one. But then the next child points at the 4 in the 1/4 and says, that's the whole bar of chocolate. Okay. So that's interesting. The 4 is the whole bar of chocolate. There's some understanding about fractions there and what that means, but what does that mean? So that's sort of emerging. Then we get someone has taken 3 pieces. So for those of us that were there, and I've been working with some teachers who were observing this, we afterwards talked about, we were starting to wonder what the children understood about the symbol representing division and what they thought that the outcome of a division was, because this notion that someone's taken 3 pieces to leave us with 1/4 doesn't relate to the notion of division when you're sharing, that this is one person's share. And so we started to wonder, even if this was 20 divided by 4 equals 5, are they understanding that in a sharing situation, 20 chocolate buttons, let's say, shared between 4 people, each person gets 5. No one's taken 15 away. Each person gets a share of 5. So it made us really wonder about the ideas they were connecting with division. So we did then get 1 bar shared between 4 people. So we're going, okay, so the 1 bar of chocolate has been shared between 4 people. So we've got the left-hand side. We feel like we've got the left-hand side sorted. But then another child says it's 1 chocolate bar split into quarters. So is that another way of saying 1 bar shared between 4? Or are they simply looking at the diagram that's in front of them and going, oh, that's a chocolate bar and I've written 1/4 on each of them, so it's been split into quarters. We want to connect this understanding. It needs to go beyond just labelling of the diagram to really understanding, and what is that connection? What is the connection between 1 bar shared between 4 and it's been split into quarters? Where is that in the calculation? Oh, it's in the same place. Okay. Did this child think the 1/4 on the right-hand side was telling you it had been split into quarters? That's part of the investigation. And then we had 1 bar shared between 4 people. They each get a piece. Nothing about that piece. Nothing about what that piece was. So here we've got a situation where we've explored in a context. We've done mathematical diagrams. We've talked and we've used all various language, contextual and mathematical, to connect it up. We've written a symbolic representation of that situation, connecting that symbolic representation back to the other representations, really hard. They really struggled to be able to explain that 1 bar of chocolate had been shared between 4 people, so each person got 1/4 of the bar of chocolate. That is quite a complex explanation, but that's the understanding that we're wanting them to have, and that's the understanding that wasn't there. So let's go back to the calculation that we saw the child in the video doing, and think about this symbol that I've highlighted, and what are the ideas we need to connect to this symbol in order to be able to do this calculation efficiently. So in the Understanding Structured Number Lines project, one of the things that we looked at was the work of Haylock and Manning, and we did some reading with that and looked at subtraction. And you'll see here that what Haylock and Manning talk about is that there's a daunting range of situations that we have to learn to recognise that connect to that symbol. That we have to know that when we see that symbol, it could be representing from this range, and that there is different language patterns connected to those different situations. Now, in Haylock and Manning, they pull out 4 structures. In different materials and different literature that you read, you will find a different number of subtraction structures. You might see 3, you might see 5, you'll see them labelled slightly differently. You might see something that here is called partitioning, somewhere else is called reduction. It isn't the labels that matter. It is the daunting range of situations that matters, and the fact that we are exposing children to that range of situations and enabling them to understand that all of these connect to this idea of subtraction. They're all represented by this symbol subtraction. But because we looked at Haylock and Manning, I'm going to look at the structures with you now. I'm just going to. So you should now be able to see some resources that I've got under my visualizer. And we're going to look at the first structure from Haylock and Manning, the partitioning structure. So this is a situation in which a quantity is partitioned off in some way or other, and the subtraction is required to calculate how many or how much remains. And partitioning is a structure that they talk about that teachers most frequently connect with the subtraction symbol. Now, some people label this reduction, and we're going to look at the Haylock and Manning definition of reduction in a moment. And what I would say looking at these is it's the partitioning structure and the reduction structure that together are most commonly connected. And often the language of takeaway is used in connection with these structures. And what they talk about here is that you can't stress enough that subtraction is not just takeaway, but often we find the word subtract substituted, and takeaway is the alternative, more often used term. So we've got an example here. There are 17 people in the pool. Here are my 17 people, and 11 get out. Oh, there's the 11 that have got out. How many are still in the pool? So you might be going, well, that's reduction. I don't mind whether you call that reduction or partitioning myself, but what you can see is there are still 17 people. There are 11 no longer in the pool, and there are 6 in the pool. But what we're working out there is how many are still in the pool. Or there's my 17 in the pool again. 11 are wearing hats. How many are not wearing hats? And so what you can see is I'm showing you exactly the same picture there, and I'm modelling it in the same way, because whether they get out of the pool or whether they're wearing hats, we've still sort of split that group between those who've got out of the pool and those that are in the pool, or those that are wearing hats and those that aren't wearing hats. So that's where this partitioning notion comes from. So the reduction strategy, similar to takeaway in the Haylock and Manning wording, but they have different language with it. So and this is much more, they think, connects with, whereas the partitioning structure connects very much with cardinal aspect of number, the reduction structure connects very much with the ordinal aspect of number. So here's our example. A swimming costume costs £17. It's reduced by £11 in the sale. What's the new price? Okay, so it's not really appropriate for me to represent that with these. A better representation is going to be something like a number line. Just going to see if I can make that bigger for you. There we go. Okay, so here what we're looking at is we're looking at 17, and it's reduced by £11. It's going down by 11. There's something about it going down by 11 here, isn't there, that we're thinking about there. So what's the new price? So that's the reduction structure. But both the partitioning and the reduction structures, as talked about within Haylock and Manning, really link to that notion of taking away. So the comparison structure is the next structure that we're going to think about. And this is very different because here we're comparing two quantities. So we're thinking about what's the difference. So there's no removing, there's no taking away. We're looking at two quantities and we're thinking, what's the difference? How much more? How many more? That's the sort of language that's going to come in here. Now, this is a really important understanding that we need to connect with subtraction. It exists in lots of situations. We need to be able to recognize it as a subtraction strategy and also as a subtraction structure. And we also need to be able to connect it with the symbol. So here's my example now. The red swimming costume costs £17, the blue costume costs 11. How much more expensive is the red costume than the blue one? Well, again, I don't think we're wanting these to do this comparison. Let's just move those a little bit. And let's see, use my bead string to help with this. Okay, so here I've got my 11 to represent the £11 for the blue costume and my 17 to represent the £17 for the red costume, and the difference between them. Here it is. How much more am I paying? So we can see that there. So that's the comparison structure. And then the fourth structure that Haylock and Manning talk about is the inverse of addition structure. And this is where we're thinking about how much you've got to add in order to reach a target. And inverse of addition is very much linking in with that sort of notion that there are inverse processes going on here. And this is going to be something that we want to draw a lot when we're working with mental and informal strategies. So here's my example. The swimming costume costs £17. I have £11. How much more do I need to buy the costume? And I'm going to use the number line to look at this, because here's my £17 and here's my £11. So how much more? And it really focuses on that part of the number line. So this is where we were looking at number lines helping with the understanding of not just number and number system, but understanding that you can then take into calculation. Is if we think about the numbers and how close they are together, looking as we are here on the number line, that it really focuses in on the difference. And actually, that's always what we're finding with subtraction. We're always finding the difference between the two numbers. But what happens a lot with children as they experience subtraction in schools is that they don't know that that's what they're actually thinking about, because the language of take away is used so much. And an understanding that that leaves you with this same gap is not always clear, because usually when children are modeling the taking away, they start at 17 and reduce from the 17. But if you look at our number line and we think about 17 and we want to take away 11, if I take away 11 from the start of the number line, it again focuses me on exactly the same part of the number line. And that's why these different situations are giving us the same result, because they are getting us to think about the distance between the 17 and the 11. So there's quite a lot to think about there. You might want to just pause and have a little moment to think about that. So this focus on thinking about the distance between the numbers, or the numbers close together, that was something we didn't see the child in the video doing until I asked them about it. So why might that be? So there has been quite a bit of research looking into this. So this comes from Torbens et al. Subtractions of the type A subtract B equals something can be flexibly solved, including what they call here the indirect addition strategy. How much do I have to add to B to get at A? So that links with that fourth structure that we've just been looking at with Haylock and Manning. And they found that elementary school children seldom use it when they're solving two-digit subtractions, which they would be working on mentally, despite its computational efficiency. So their study is showing they're not choosing it, they're just not choosing to do it. And McClellan here talks about the fact that if we don't teach that can be a procedure that gives you the answer to subtraction operations, they aren't going to choose to do it. So this is part of the reason maybe behind what Torben and others were finding in their study, is the fact that they're not being taught that is a way that you can think about subtraction. It's not one of the ideas they're attaching to the subtraction symbol. And it didn't seem to be one of the ideas the child in the video was attaching to that subtraction symbol until I prompted that. And what can happen, what McClellan talks about here, is the time it takes for a child to discover that, then they may have been doing things inappropriately, or they may have been missing efficient ways of doing things for quite a long time. And that might be one of the reasons that subtraction then starts to feel harder than addition. I think that's interesting to think about the impact of that. So we want children to be aware of this. Then we might need to use different language when we're looking at subtraction. And that takes us back, and different thinking, that takes us back to the Haylock Manning. So when I say different language and different thinking we want to attach to it, then this becomes a key question. How close together are these numbers? The question I asked in that video, are these numbers close together? And how close together are these numbers? Is that a question? That point of noticing, when I'm faced with a subtraction, do I ask myself, or do I notice whether the numbers are close together or not? And does that then trigger something? So what this does is, if we're thinking about indirect addition, the fourth of the structures that Haylock and Manning talk about, it prompts this question: how close together are these numbers? And then this links to understanding number and the number system. And you'll see, I hope, how this links with what we were looking at with structured number lines, the relationship between the numbers. And that's one of the things that structured number lines can support, is that understanding of the relationship between numbers in the number system. So then there are other ideas when you start to engage with this that start to emerge. You can start to generalize, and you're generalizing and you're thinking about the number system. So ideas that you're generalizing from rather than actions. So what you start to notice is, well, the closer together the numbers are, the smaller the difference between them. Oh yeah, I can look at that on my number line. So if I move closer to the 17, the difference becomes smaller. That's what happens. So, oh, well, that means there's another notion here that we can think about, which is the further apart the numbers are, the greater the difference between them. So we're building up now some sort of generalizable understanding that comes from thinking about and using different language attached to this symbol. And then what that gets us to is to thinking about, well, what about maintaining the difference? So I'm just going to switch my camera back to the visualizer. Let's just get my number line underneath it again. So here, I'm just going to try and make that bigger for you. Okay. So here is my difference between 11 and 17. 17 is 6 more than 11. Well, if I move that, oh, look what happens. I've got the same difference between 18 and 12. I've got the same difference between 19 and 13. I've also got the same difference between 10 and 16. So now I can start to think about this really fundamental bit of understanding of subtraction, which is, how do you maintain the difference? You either increase both numbers by the same amount or decrease both numbers, but you're seeing why that is. That doesn't allow you to understand equivalent subtractions unless you understand that subtraction is about finding that gap between the numbers, that all the different structures, you still end up finding the gap between those numbers. That's where we get to. So we get this generalization at the bottom, that maintain the difference results in equivalent calculations. So we can therefore adjust 603 subtract 598 and say that that's the same as 605 subtract 600. And sometimes understanding equivalent calculations allows you to solve a calculation very easily, because you can make an easier subtraction than the one you've been presented with. So this all stems from thinking about that indirect addition or that inverse of addition structure, prompting this question: how close together are these numbers? So Whilst I'm saying that I don't think children experience this very much, it does exist in materials that we have. So, for example, in the Teaching for Mastery questions, tasks and activities to support assessment materials that were produced in 2015, in the year 4, in one of the big ideas in subtraction, looking at the numbers in a calculation and their relationship to each other can help make calculating easier. Exactly what we've just been looking at. For example, 3012 subtract 2996. Noticing that the numbers are close to each other might mean this is more easily calculated by thinking about subtraction as difference and solving it using that indirect addition idea. This takes us back to here, doesn't it? It takes us back to connecting the symbols to the experiences. But one of the things I think was interesting about the child in the video was that he did know that those numbers were close together. And he did know how to work that out. So he was able to look at that gap. What he didn't understand was that experiences that he has had, and he's had experiences of solving problems where the numbers are close together, that those are things that he should associate with that symbol. So how do we've thought about this, how we're connecting from the context language and structured images up to the symbols and checking that understanding. But what I want to think about is, how do we go from the problems themselves and make that connection? And I'm wondering if there is an overemphasis on finding solutions to problems in our classrooms sometimes. And it doesn't matter how you got to the solution, you got to the correct solution, that's celebrated. And if what you're recording are the steps that you took to get to that solution, how absolutely fantastic. And no time is spent looking at, but what is the way that we would symbolically represent this problem? What's the calculation that actually matches the problem itself? So I'm going to look to Japan to help us with this, and that's what we did in our study as well. So I've been very lucky to have visited Japan as part of the Impulse program, and this is the immersion program. So it's a chance to go to Japan and to visit classrooms and to see research lessons that have been very carefully planned. All their professional development happens through lesson study, and the planning team over a number of sessions creates a research lesson using existing materials as their starting point, really exploring the understanding and the meaning behind those materials, and then designing the lesson. And then there's a research lesson that many people attend, and process and discussion. And that just tells you a little bit about the Impulse program. And if it's something you're interested in, I've put a link at the end. So when I was in Japan, the first lesson I went to see was one in grade 5, which is year 6 here, focused on division, division with decimals. And this just takes you from the unit what the focus was and gives you a little bit of a sort of knowledge around that. And interesting when I think you look across and they've got the mathematical way of thinking, they are thinking about the meaning of division by decimal numbers, by connecting to their prior learning. So it's about the meaning. And one of the things, if you look in that second column that we've got, is the second bullet point, that the children were being asked to set up an expression and think about why it is appropriate. Why is that what we should be thinking about? And the mathematical question for the lesson was, is 300 divided by 2.5 the appropriate calculation to find the price for 1 metre? So context that was in the lesson, on the right hand side you've got as it sits in the textbook. They didn't open the textbooks for this. The teachers set this up and they explored it all as a class and on the board and in their own books. But it was prompted by this, and the planning team had started with this problem. So the teacher had a rolled piece of ribbon, and she said, I asked my colleague to buy me 1 metre of ribbon at the market yesterday. And then she unfurled the ribbon, which was clearly longer than 1 metre. So the children were going, that's not 1 metre. Oh, that isn't a metre. How long is it? Etc. So we're already engaged, and we've got the fact, and we find out that it's 2.5 metres. And the teacher says, this cost 300 yen. So I'm only having 1 metre of it. So how much do I need to pay? How are we going to work it out? What's the calculation that tells us what we should be working out, what it is, what this problem is? And so the whole lesson was not about how much have I got to pay my colleague. It was about, is this the calculation, and why is this the calculation that matches this context? And how do we connect that with our previous learning? And what I'm going to show you is the board work that resulted from that lesson. And obviously it's in Japanese, but you're going to notice some interesting things. But if you look at the bottom of the left-hand side, there is that key question with a question mark. Is it 300 divided by 2.5? Is that the expression? Is that what we're going to try and work out? You'll see in the middle, the connecting with prior learning and thinking about whole numbers. You'll see that the double number line is used, and that's referenced in the plan as well. But then we end up with something equals 300 divided by 2.5. There's our key question again, but looking at it the other way around. So this whole lesson was really focused on what's the calculation that matches the problem. And one of the things I reflected on was, I just don't think that that happens very often in this country, but what an intriguing thing to look at. So we did exactly that. In our Understanding Structured Number Lines project, we did a cycle of collaborative lesson research, which is Japanese style lesson study. And the planning team came from a group of schools that were working on the project. So we had a number of schools working on the project, and they were all invited to have at least one teacher involved in the planning team. And the planning team met and worked together over 4 sessions, as you can see set out here. And there is all detail about this in the report, but I'm just going to look at a couple of specific things within this here. But what you might notice as you go down is that planning team spent a lot of time together working on this. Now, in the first session, we just looked at and explored the mathematics, and then we looked at the Haylock and Manning reading and the problem that we were going to work with, and started to go from there and to plan the lesson. And then we had sort of 2 full sessions really pulling together the research lesson. So it's worth knowing about the children in the Year 4 class that were going to be taught. We did some assessment questions with them, and like the children in the studies that I've mentioned, Corbyn's study, for example, for the calculation 552, subtract 548, none of them chose indirect addition. 73% of them did a written method. So 73% went the route that we saw the learner in the video go for the calculation he was doing. And of those 73%, only 36% were correct. So only about a third of the children who chose to do it in a formal way actually got the correct answer. And then 20% partitioned, and all of those children got the correct answer. And that's what we saw the child in the video do. That's the way he ended up doing it. He partitioned the second number, didn't he? He subtracted the 500, subtracted the 90, subtracted the 8, and he was successful. So the partitioning did lead to success, and the written method on the whole didn't lead to success, but nobody chose the indirect addition. And the planning team then sort of looked at this calculation. They thought about this calculation where the numbers are close together, and they thought, what's all the knowledge and understanding you need to solve this efficiently? When I asked you to solve 603 subtract 598, I asked you to think about that. What all the things you need to know and understand? And these are some of the things that the teachers identified. You need to know that 82 and 77 are close together. Do you have that sense of those numbers in the number system, that they are close together? You need to know that you can solve that problem by finding the difference. You need to attach to that symbol, subtract, ideas. And one of those ideas is that you can find the difference. You need to know that both 82 and 77 are close to 80, and that lies between them. And therefore it's an easy step from 77 to 80. And you're using something that's a known fact here, 7 add 3 equals 10. And then it's an easy step from 80 to 82, and that uses place value knowledge. 80 plus 2 is 82. You need to keep track of those steps. The fact that you've done add 3 and add 2. You need to know that those 2 steps together show you that gap between 77 and 82. And you need to know that the 3 and the 2 are going to give you the 5. So there's a lot to understand and to bring to this, to be able to do that efficiently. Now, the child in the video had no problem, I think, with any of those except the second one. he could choose to solve the problem that way. That is not what he had understood, and that's what we were interested in. So this was the problem that the team looked at initially. What I want to do is look at part of a transcript from this first session where they worked on this, and then they talked about how they'd solved it. And then they were asked to write down the calculation that matched the problem. And this is the transcript. So the person leading the session said, and then how did you get 30p? I thought about the difference between £3.50 and £3.80. And you didn't, when you said I thought of the difference, what you've done, I don't know if you can see, she's showing it to everybody, you've put a little line between there. Just agree with the person next to you what calculation Claire was doing. So there's a picture there of what the teacher had written as to show the calculation, but she hadn't actually written a calculation, so that went with the problem. And so what is the calculation? And there was a lot of discussion and a lot of time before we got to the PD lead saying this next bit. What I'm trying to get you to notice is that when you were doing this calculation, this bit is a subtraction. This bit of finding the difference you can represent with a subtraction. So interestingly, the teachers found that difficult to connect. So when the numbers were close together and we were exploring those subtractions with them, where they chose to solve a subtraction using addition, they also wrote to solve. So you've got a problem and the numbers are close together, so they solve it by using an addition. They would record the addition, even when asked to record the calculation that matches the problem. So they were writing the calculation that matched the method chosen for solving the problem. So what we're realizing is if teachers are not recognizing that themselves, and possibly the importance of that, it's probably not going to be happening in the classrooms. So in the discussion about this and thinking about the Haylock and Manning reading, the teachers found it really useful to go back to this bit from Haylock and Manning to help us connect those structures, is to ask this question: what's the calculation I would enter on a calculator in order to solve this problem? So if we go back to the difference between £3.50 and £3.80, to find that out on a calculator, you would enter 3.8, subtract 3.5, and that will give you your answer. So the subtraction symbol and the notions of subtraction emerge when you think about that question. So this led us to planning our research lesson, and this is the not so neat board work that I did as I was the teacher for the research lesson. And just to give you a little story across that lesson, we started with the numberless problem, which you can see on the left there. Every week I buy bottles of orange juice. This week the supermarket has a special offer. We've done some work around the languages special offer, and we revisited that. And then they asked questions. They had questions. You know, it's not a mathematical problem yet, so they want to know how many bottles of orange juice, how much does each bottle cost, what's the special offer. So then these were the numbers that the teachers ended up deciding on for this lesson, that the special offer would be 2 for £2.39, but a single bottle of orange juice would cost £1.30. So each week I buy 2 bottles of orange juice that cost £1.30. Special offer this week, 2 for £2.39. How much am I going to save this week? So we explored the finding out of the cost of the 2 bottles of £1.30 with the children. You'll see at the bottom there, some talked about it as addition, some talked about it as multiplying by 2, as doubling, and established that £2.60 was the price of the 2 bottles of orange juice. And then we get to the interesting bit. So the interesting bit is the difference. And what we wanted them to do was to think about how they solved it, but then think about, but what was the problem asking us, and how would we write that problem down so that it would enter it into a calculator? Exactly what we've just been talking about. So what we found, I'm hoping if I move myself here, that allows those to be seen by you. What we found is a difficult part of the lesson that we anticipated was a difficult part. Many of the children solved the problem. Many of the children found that you're saving 21p. But when asked to match the calculation to the problem that we'd had, which was the difference between the normal price and the special offer, we got either additions written down, so that middle one there, £2.39 plus 21 equals £2.60, or we got a subtraction that involved taking away the saving. So they were thinking about how much has been taken off the £2.60. They were not thinking about the comparison between the £2.60 and the £2.39. So this is obviously something that needs quite a lot of work, and we need to sort of continue to work on with the children. We did use a sentence starter, I have noticed, for the children to look at the end of the lesson, and that provided another opportunity to reflect on connecting the problem with recording it symbolically as a comparison subtraction. And we did have some children that did that. We've got two here. One who's said, I've noticed that 21p is between £2.39 and £2.60, and then they've shown that, those arrows on their number line. And then I've noticed there is a difference of 21p from £1.30 multiplied by 2 was £2.60, and the special offer of £2.39. So we've got that word difference coming out there as well. So noticing it's between and noticing its difference. But there was a lot more potential with that than we fully realised, and that needs to be exploited more with those children. And this was where we ended the lesson. This was the understanding we were working on, and we were only working on it. We had not achieved it. We were definitely working on it. But the comparing two prices is subtraction. That is what you are doing. If you are comparing two prices, that is a notion that attaches itself to subtraction. It's one of the ideas we need to know, we can think about when we see that symbol. And then when numbers are close together, it's often easiest to solve the subtraction by adding on to find the gap between the two numbers. So what happened in this lesson was many children solved the problem and found the difference by adding on. They just did not connect that with £2.60 subtract £2.39. So this idea of having lessons where we really explore what's the calculation that matches the problem, not just how we solved it, what's the calculation we put into a calculator, seems to be a really useful thing to think about. So I'm just going to summarise what I've looked at with you here, and the things that I'm hoping might resonate with you and might give you things to go away and think about and to work with in your own situation and setting. So I'm going back first of all to fluency. What is fluency? This notion that it involves noticing things, making connections between what's known and unknown, and then making decisions based on that, and that decision making is absolutely vital. So my second bullet point there is that calculating should involve decision making. So there should be a pause. There should be okay, how am I going to solve this? Oh, I just know the answer. Oh yeah, the best way to solve it is the written method. I'm going to go to that one. Oh no, hold on a minute. I think I've just noticed this. So this means, and I'm going to work it out mentally. That decision making. Symbols, looking at our lovely connective model there, they need to be connected to ideas, not just words and actions. So it isn't good enough that children just label symbols and they say parrot a word and they do the same thing every time they see that symbol. That's not good enough. We need to be connecting it to ideas, and there's a whole range of ideas that are going to be connected to different symbols, and particularly the operations. So that connecting up the symbols, language, context, mathematically structured images, which might be concrete, they might be pictorial, though all of that needs to happen. And when we're connecting up the symbols, it's really important that we don't overemphasize one idea and reflect that in one particular type of language. So in the particular example of subtraction, I think at the moment there's an overemphasis on partitioning and reduction structures. I'm going to plump those together, and that's reflected in the overuse of the language takeaway. And takeaway is almost used as the generalized term very often for subtract. That's not helpful. It's not helpful in building up those ideas, and it's not helpful in being flexible and being fluent. Solving problems, we want to include understanding the calculation that reflects the problem rather than just focusing on the calculations used to solve the problem. And those useful questions that have come up during the session: what would you put in a calculator to solve this problem? What is the calculation that gives the answer? So in the session with the teachers, the person leading the session, when she was trying to get them to recognise that you could write that as a subtraction, wrote up equals 21p. What's the calculation that gives us equals 21p? That's the answer. What's the calculation? And then just for subtraction particularly, ensure that children are taught to consider how close together are these numbers. And that is a much more useful default thought than thinking about taking away. But we want them to connect lots of ideas. So I hope that's been useful. I hope that's been interesting to you. The slides will be available, and what you'll see on the next two slides are references. Some of them have links to things that are available where it's available online. So those are the references. But I've also put 4 links on here that you might be interested in for further thinking and exploration. I've talked about collaborative lesson research, that Japanese style lesson study that's happening here in the UK, and there is a collaborative lesson research UK charity, so there's a link to them, and they have events that happen. The Impulse program I mentioned, which is that immersion program in Japan, that program is sort of carrying on, and they've also been doing some online sessions as well, so there's a link to find out more about that. I mentioned executive function early on after the video, but didn't go into any depth about it. If you're interested in finding out more about that, there's a webinar that I did with Camilla Gilmore, looking at that very same video, but analysing it from an executive function point of view. It's an introduction to a research innovation work group with the Jurassic Maths Hub, but it's applicable, it's of interest to people beyond the people that were going to be in that group. And the understanding structured number lines, if you want to know more about the number line and the structured number line part of that and what we found out, there is a webinar about that as well. And you will see my contact details there. Please do get in touch. There's my website, there's my email, and also my Twitter handle. Thank you very much. And I hope that's been useful, and I look forward to hearing from any of you who would like to sort of share your interest with me. Thanks very much.